All right, so did you guys have any questions about the homework? Or anything we covered last week in particular? Was that a yes? The bike one on 5.1. Let me see here. Sure. Can look at that for a second here. So number 59. We have a bicycle with a 24-inch diameter wheel traveling at 15 miles per hour. All right. So it's 15 miles per hour, right? And 24-inch diameter wheels. All right. You're supposed to find the angular speed of the wheel in radian. And what else? How many revolutions per minute? Okay. Let's see here. So the key idea is that the relation between, well, first of all, if the diameter is 24 inches, right, the radius is what? 12 inches, right? So that's one thing we know. We also know that there's a relation between the linear speed and the angular speed, right? So linear speed is equal to the radius times the angular speed. All right, so linear speed is 15 miles per hour. So let's see here. So this gives us omega, the angular speed, is v over r, right? Now it just becomes a somewhat annoying question of unit conversion, right? So let's see here. We've got 15 miles per hour, right? That's the v. And then we're dividing by what? R, which is 12 inches, right? So we either need to convert miles. We want to get the seconds, right? I'm going to go for radians per second. So I need to think about how to convert the units, right? So some useful things to know. A mile is 5,280 feet, right? And a foot is this, we all know, 12 inches, right? So I can change this to, let's see here. So a mile, I'll do the kind of thing I did last time, which is to multiply by 1. All right. So let's see here. Mile is 5,280 feet is equal to a mile, right? And then 12 inches is a foot. So that will cancel the feet, that will cancel the miles, right? And what am I going to be left with? We'd left with radian, right? Because It's not written there, but that's what it is. And I need to convert the hours to seconds, right? So how to get rid of this hour? Let's see here. I multiply by 1 again. Yeah. Inches for the radius. Yes, 12 inches. You're fine. So the hour is already downstairs. I want to cancel it out, so I put the hour upstairs. Like I want to multiply this by hour and the number of seconds in an hour. How many seconds are there in an hour? Well, 60 times 60, right? There's 3,600 seconds in an hour. So this is the game you play. Multiply by 1, factors of 1 that cancel the units that you don't like and give you the units that you do like, right? This is the game we can play. Now, if you know a different way to think about unit conversion, I don't mind. I mean, like, this is my way of doing it. You might have a different way of doing it. That'd be fine. But as you can see, this inch and that inch cancels, and we're just left with a pure number, which over seconds, which is radians per second. So whatever that works out to. What we got? Of course, if I was smarter, I would have, instead of multiplying by 12 and dividing by 12, I could have just canceled the 12s. Not been an idiot, right? Duh. I get 22. 22 radians per second. Right? Now, how do I convert to revolutions per minute? So I take 22 radians per second, and I multiply by revolution per 2 pi radians, right? That's the conversion between revolutions and radians. 1 revolutions per 2 pi radians. And I want to convert the seconds to minutes, right? So how many seconds are there in a minute? Right, so I multiply by 60 seconds over 1 minute. So I got 22 times 60 divided by 2 divided by pi. I get 210.1, roughly speaking, RPM. Now this was number 59, right? So I think odd answers are in the back of the book, or the back of the PDF. Let's see here. Moment of truth, right? Yee! Oh, they give it in radians per minute. Those idiots. 210, but I do have 210.085 revolutions per minute. So the book agrees with me on the RPMs, and apparently it asked for radians per minute. Oh, it did ask for radians per minute. I can't read the question. I made it radians per second. I solved the harder problem. Sorry. But does that make sense? Okay. But yeah, the main thing is just the relation between the linear speed and the angular speed is this. Once you know that, everything else is just unit conversion stuff, which I'm starting to regret putting into this course. Because it's really, I mean, it is an important skill for all of you to like master because you have science courses, right? And this is where mathematics and reality come together, right? Like, for example, I think the Hubble telescope had to be retooled because somebody didn't keep units with a number. Like, we wasted like millions upon millions of dollars needing to like retool it because they put meters instead of centimeters, something like this. Like, units really do matter. And I can tell you, I worked for the Navy for a year in like a research lab, and a lot of times, like the units do get lost in the shuffle. Like it is something that happens. So, actually, a good practice in industry is to like put the name of the unit into your variable. So if you've got like position in meters, your label should be something like x underscore meter or something, just so that you know it should be explicitly labeled. We never do that in mathematics, right? We just say x. We don't say x in feet or x in dollars or whatever. Other questions? Well, the homework is not really due until the test. So you have till the test to complete it, but the quiz will be based on the homework that it would have been reasonable to finish. So like the quiz Wednesday should be based on the homework that I assigned last week. So it wouldn't be on the stuff we're doing today, although I think you wouldn't mind it being on the stuff we're doing today, because the stuff we're doing today is super nice and very, I think the stuff we're doing today is cleaner than the unit circle things, because there's no like, well, a lot of it is, there's nothing about minus signs or quadrants. It's just about like a right triangle and thinking through it.
We'll have that note card on this quiz, right?
Yes, that is right. You can bring a note card, but otherwise it is closed notes, open homework. So you are allowed to look at your homework during the quiz. Yes. But I need to look at your notes, because I have to like, this is like during your quiz, I look at your notes and make sure that you've taken notes. And if you've taken notes and they look like quasi-reasonable, I'm going to give you full credit for that, right? It's not some, I'm just trying to do my due diligence and try to encourage you in taking notes, because there is a subset of students who just kind of like check out in class, but it's not happening here, so these measures are kind of unneeded. But it's what I said I'd do, so I guess I'll give you those points. Right. All right, well, let me erase this and get into it. So we've talked about sine and cosine and well, we haven't talked about tangent really, but I want to talk about the trigonometric ratios. Ratios for a triangle, really a right triangle. All right, so here it is. So this is a right angle by assumption. Make that little thing there to indicate 90 degrees, right? And I'll call this angle over here theta for the sake of discussion. All right. Now, I don't mean to say it has to be the standard angle. It's just an angle inside a triangle, right? This triangle could be tilted or something just the same, all right? And so then we'll talk about this being C, this being A, this being B. But alternatively, you could use the labels, as I told you guys last time, opposite. In fact, we'll use this language, the opposite side, the adjacent side, right? And of course, C is the hypotenuse. So what do we know about right triangle? Well, we know the Pythagorean theorem, right? We already know that. A squared plus B squared equals to C squared. Certainly that's something to keep in mind. Good to know. But we can also define 6 interesting trigonometric ratios for such a triangle. What are those 6 trigonometric ratios? Well, I'll start with sine. Sine theta is B over C, right? It's the opposite over the hypotenuse. Cosine theta, A over C, right? It's the adjacent over the hypotenuse. Tangent theta. Tangent theta is, well, opposite over adjacent, right? It's B over A. All right, now, before I go any further, let me just point out something obvious about tangent. We could rewrite this as what? We could write this as b over c, right, divided by a over c. Right, divide the top and the bottom by c. Then what you got? You got sine theta over cosine theta, right? So an alternative definition of tangent is that tangent is the sine of theta divided by the cosine of theta. So this is tangent. All right. And then, in addition to this, we have the reciprocal functions. Reciprocal trig functions. So we have CSC, which is for cosecant. Cosecant theta is 1 over sine theta. Secant theta, 1 over cosine theta. So notice that the pattern is kind of the opposite that you want it to be in terms of like the alphabet, right? The secant corresponds to the reciprocal of cosine. The cosecant is the reciprocal of sine. That's how I remember which one goes with which, personally. It's the break in what I'd expect. You know, cotangent theta is 1 over tangent theta. Now, of course, all of these ratios we can express in terms of the side lengths of the triangle as well, right? Like it's 1 over what? The first one, the cosecant, it's 1 over, you know, the opposite over the hypotenuse, right? Which is the hypotenuse over the opposite side, right? And likewise, cosine is 1 over the adjacent over the hypotenuse, which of course works out to the hypotenuse over the adjacent side. And tangent, I don't know why I'm not using A, B, and C. I guess it's just because I like writing. But if I was lazier, I would be using the ABC notation, but I'm just a glutton for punishment here. But the cotangent is the adjacent over the opposite. So these are your basic trigonometric functions, right? And what are the fundamental identities that we know for sine, cosine, tangent, cosecant, secant, and cotangent, right? The fundamental identities that we know. And these can be useful for figuring out one from the other, right? As I mentioned last time, if we divide this by a, by c squared, we've got a over c squared, right? Plus b over c squared equals to 1, right? Notice that if I divide the Pythagorean identity by c squared, I get this. So this gives me, well, I could do that, right? What else could I do? I could likewise divide it by what? What if I divide by like a squared? What do I get? I get that, right? What's the other thing I could do? Divide by what? B squared, right? That would give me a over b squared plus 1 equals to c over b squared. Now, tilt your head and squint there and see if you can tell me, well, I'll do the easy one. The middle one is, of course, the famous cosine squared theta plus sine squared theta equals to 1, right? Good to know. What's this one? A over b is what? No, I didn't. I should have written it. This is a over b, right? This is c over a. This is c over b, for what it's worth. So like this one, a over b is cotangent. So this is cotangent squared theta plus 1 equals to what? C over b is cosecant squared. So that's the identity that links cotangent and cosecant. And then this one over here, b over a. Well, b over a is tangent, right? So this is the identity 1 plus tangent squared theta. C over A is secant, right? Secant squared theta. Now, so these are, I would call every one of these a Pythagorean identity, right? This is the relation between these fundamental trigonometric ratios. If you tell me like a little bit of information about a triangle, we can use the trigonometric ratios and these identities to like piece the rest of it back together, like, right? Like a forensic investigator of triangles, you know, or something like that. I don't know. It's a stupid example. Wait a minute, it's not stupid. So here's one. Let's see, here's theta. Suppose this is 3, suppose this is 4. Find the trigonometric ratios. Find sine, cosine, tangent, cotangent, cosecant, and the rest. Find them all. You gotta catch them all. I'm sorry, that was horrible. I apologize for nothing, though. All right, so I will write the solution in yellow. So what's C? First thing I would do is figure out the hypotenuse, right? So C is going to be the square root of 3 squared plus 4 squared, right? Because we can take the square root of the Pythagorean identity to solve for C, right? So that's what? That's 9 plus 16, which is 25. Square root of 25. I heard 5. Very good. Yes, of course, this is the famous 3, 4, 5 triangle. So in fact, yes, C equals to 5. We figured that out. Now it's a simple matter. What's the sine of theta? What's the cosine of theta? You guys tell me. I have 4/5, yeah, 4 over 5. 3 over 5. Tangent theta? 4 over 3. Yeah, flip them, exactly, flip them. So this is I got to watch myself here. Cosecant theta is for 5/4, right? Secant theta, 5/3. Cotangent theta, 3/4. All right. Any questions? Still owe you guys a handout of the unit circle thing. I will eventually remember to hunt that down. I have like a folder somewhere at home with a big one in it. I should just ask Professor Giles. I'm sure she has like a giant one I can copy, but yeah, I think I probably should give you that sheet as like an addendum. So I should provide it for you though. Otherwise, it quickly becomes a sheet of notes as opposed to a 3x5 card of notes. And a sheet of notes, unfortunately, I believe, this is my speculation on the basis of last year, I think a sheet of notes has the tendency of giving students the false sense of security that they do not need to study, which is in fact false, right? It just seems like that. But the thing is, like, even a sheet of notes, if you haven't actually, like, if you're just hastily preparing it right before the test, right, and you don't really know it, it's not going to really help you that much, actually, right? Now, personally, I had classes, like junior level physics classes, where I was allowed a page of notes. And if you look at the pages that I found these, you know, the pilot pens, like the metal, yeah. So I had like that kind of pen, and I'm writing in like size 6 font, and it's the whole thing front and back. But I remember having that, right? Because you never know what kind of calculus is going to come up in the middle of a junior level physics test. I mean, they can just ask you to integrate sine cubed off the top of your head, stuff like that, right? Whatever that means. You guys haven't had calculus yet, right? but you will soon experience this. It's not that bad, actually, but it just takes time, right? It's easy to forget some particular detail, especially trigonometry. But I remember, writing these, spending hours constructing these formula sheets, and then I get to the test and not even use it. just like, because the process of writing it out had like ingrained it in my mind, right? I also remember just taking one test and just staring off into space for like 20 minutes, having no idea what to do. That is a bad feeling. But the thing is, I was being very foolish, right? There were 3 other problems I knew what to do. But that one problem I was completely stuck on, and I just couldn't let go of it, This is very, very bad behavior. Anyway, I digress. Oh, here's another problem. So let's suppose we have, sorry, all my triangles kind of look the same, but suppose this angle is pi over 6, all right? And we know that this is 7. Find, let's call this B and let's call this A again. Find A and B. Different example than the first, right? So here I'm inviting you to remember, well, something I will tell you logically. The cosine and sine I'm defining today in terms of trigonometric ratios is in fact the same sine and cosine that we talked about in the unit circle. Everything we did for the unit circle sine and cosine is still true here because they're the same sine and cosine. All right. Okay, so we figured out the cosine of pi over 6, right? Last time. We figured out the sine of pi over 6 last time. I'll remind you, we worked out that the sine of pi over 6 is a half. We worked out that the cosine of pi over 6, radical 3 over 2. So, let's think through it. So those are equal to the trigonometric ratios, right? Those are equal to what? Opposite over the hypotenuse, which in this case is 7. The adjacent over the hypotenuse, which in this case is 7. So now we just have to solve those Math 101 equations, right? So this tells me what? This tells me B is equal to 7 halves. And this tells me that A is equal to 7 root 3 over 2, right? There you go. We figured out the rest of the triangle because we already know the values of sine of pi over 6 and cosine pi over 6. So, remark. Okay, so we have like a triangle, and I just keep drawing them like this because it's just, here, tell you what, let me draw it the other way. It doesn't have to be that way. I don't mean to indicate that the triangle has to look like that. Like it can be tilted, it could be all kinds of different, let me draw it a really weird way. It could look like this, okay? This could be theta, right? And I'm level adjacent side, opposite side, hypotenuse, right? So it's still the case. Cosine theta, A over C, sine theta, B over C, tangent theta, B over A, right? But I would point out, perhaps of equal importance, and I use these all the time in applying trigonometry to figure out things about triangles, lengths of triangles. I oftentimes find myself using what I'm about to write even more than the definitions for the function. I mean, distinguishing these from the definitions, it's almost silly to do so, but oftentimes this is what we need, right? A is equal to C cosine theta. B is equal to, c sine theta. And then, of course, b is equal to the a times the tangent of theta. I almost prefer to write these equations in terms of the other language, right? Like the adjacent side is the hypotenuse times the cosine theta. The opposite side is the hypotenuse times the sine theta. The opposite side is also the adjacent side times the tangent of theta, right? So these are very useful, intuitive guides as we're working problems, like trigonometric problems. I use these all the time, especially in physics when I'm breaking vectors down into pieces, right? So like example 3. Find lengths of unlabeled sides. So here, suppose I got, suppose this is 3. I'll get out of the way here in a second. This is 20 degrees. There we go. If that side length is 3, and I know that that's 20 degrees, can I find the lengths of the other two sides? Now I'm going to have to use my calculator on this one because 20 degrees is not a special angle, right? I'm not just going, oh, it's a half or root 3 over 2. It's not one of those, right? 20 degrees is something else. So when I have a problem like this, I give labels to the things I don't know, right? Just to try to keep myself honest. And so like what I don't know here is, I'll call it A, and I'll call it C, right? So which trig function should we use to get our pause on A? Like what's, yep.
You find all the other angles inside. Because you're right, so it's 90.
Ooh. Yes, we could do that. So, I mean, if you want to do it, you want to do it that way? I mean, you can if you want to. I'm about to talk, that was the next thing I was to talk about is looking at the other angle and thinking about the trigonometric ratios, how they're related for one angle and the other. Let me pause that for a second. I mean, I totally agree. We could look at the 70-degree angle there and kind of go from there, sure. But if I'm just stuck with just constrain our thinking to this 20-degree angle for a second, how would I get, what should I look at to relate 3 and A? That's the opposite. That's the adjacent, right? So tangent theta is the one to go with, right? So, in fact, I have it right here, right? Oh, but I did it the wrong way. So let me just write it down. It's not the wrong way. It's just not helpful. So tangent of 20 degrees is equal to what? It's equal to 3 over A. So solve for A. What's that give us? A is equal to 3 over the tangent of 20 degrees. Let's see if we can figure out what the tangent of 20 degrees is with our handy-dandy calculator. You do need a calculator for the next test, right? Like I will have some non-special standard angle stuff. So you got to be careful. Like my Casio, there's a song about this, you know. Mine is an R, which is not for like a pirate mode. It's for radians. Sorry, that was horrible. How do I get out of radian mode, though? That's a question. Huh. Degree. I found it. So I had to I think I hit mode. I might have hit shift mode. I can't remember. But that little R will change to a D on mine. And then I go tangent. I'll put 20. Oh, wait a minute. What am I doing? 3 divided by the tangent of 20, right? And that gets me 8.2424. I'll just keep the first two. There we go. I just keep 4 numbers as a point of habit. But so 8.24 is this side here, right? 8.242, roughly speaking, A. Now, how do you figure out C? That's right. I mean, you could use one of the other trig functions because the trig function, you could use sine or cosine of 20 because those do relate. The hypotenuse and, I mean, you could use one of the other trigonometric functions, but I like what you said. Use the Pythagorean identity. C is equal to the square root of 8.2424. So 2.24. I'll keep the 2424 this time. Just beware if you truncate if you approximate one of the side lengths and then you make the next step, you're going to get rounding error there, which I will not generally count off for if your heart's in the right place. But do be sensitive. There are problems where it actually matters to keep a bunch of digits. Where would that matter? So I got 8.771. So the place where you got to keep a lot of digits is if you're working with something where you have 2 of the sides of the triangle are really, really close to the same length. There, the digits start to matter. Like, for example, if you're trying to find cosine of theta for a triangle which has an angle which is really, really close to 0, to gain any kind of confidence on that answer, you're going to have to keep a lot of digits because cosine of 0 is 1, right? And so let me just show you what I mean with an example. Suppose you're dealing with this rather silly triangle. Suppose this is 1. This is 10. And of course, this is the square root of 101. If this is theta, cosine of theta is what? Well, it's the adjacent, right, over the hypotenuse. What is the square root of 101? Yeah, so this is approximately 10 divided by 10 point, let's say 0.5. All right, so I'll just round that. It's like 4987562, whatever. So what's 10 divided by, so I'm going to do it. 10 divided by 10.05, what's that? I get 200 over 2 to 1. That's approximately 0.995, right? Let's see here. On the other hand, what if you just calculate 10 over that directly in the calculator? Same thing. Curses. Yeah, man. I've not been careless enough for me to make my point. Sorry. This example does not serve the point I was trying to make, but it is an example nonetheless. So sorry. So any questions about what we're currently doing? All right. Let's try to do something a little bit sneakier. All right, so here's the question. So a bunch of the homework in this section is like use reference angles to calculate various expressions, all right? So let's look at one of those, like secant of 7 pi over 6. So what are we going to do here? So I guess I should confess at this. Be like, whoa, hold on there, flag on the play. You were just talking about the trigonometric ratios in terms of right triangles. Now you've thrown this in my face. This is not a right triangle. This is 7 pi over 6. That's like a standard angle that's beyond 180 degrees. You know. All right. So confession. We can define tangent and secant, cosecant, cotangent, all these functions by the identities I wrote and erased here, right? Like tangent is sine over cosine, secant is 1 over cosine, cosecant's 1 over sine, cotangent's cosine over sine, right? And so because we can define sine and cosine for all angles around the unit triangle, we can also define all of these other trigonometric ratios, right? So since we know how to figure out cosine, well, we can figure out cosine of 7 pi over 6, right? So that's the question. So we know that secant 7 pi over 6 will be equal to 1 over the cosine of 7 pi over 6. Let's see here. Let me draw a picture. Where is 7 pi over 6? So, yeah, it's like exactly, it's like 210. It's over here, right? So if I use that theta prime notation like I did last time, I believe, for the reference angle, what's the reference angle here? Yeah, 30 degrees. Pi over 6 radians, right? So, so if I think about this right here, right? This is, like you said, 30 degrees. So that makes this side length 1/2. It makes this one square root of 3 over 2. If I put a 1 here, right? By the 30 degree, 30-60 triangle. So my question is, if these are the lengths of the sides, right? And the point we're looking for on the unit circle is like over here, what are the coordinates to that point? It's square root of 3 over 2 horizontal, right? And it's 1/2 vertical. And it's in quadrant what? Quadrant 3. They're both negative. So we'd write minus root 3 over 2 and minus 1/2. Now, remember, those are what? Cosine theta, and this is sine theta, right? Now, we want 1 over cosine theta for secant, right? So secant theta, 1 over cosine theta, and that is 1 over minus the square root of 3 over 2, right? So therefore, we have secant of 7 pi over 6 is 2 minus 2 over the square root of 3. So all of these problems in the homework can be solved in this way. Like, you just look at the standard angle you're given, and you can use the special triangles and the reference idea to figure out sine or cosine, and then just flip it if it's as needed to get back to secant or cosecant. Or
Does it have to be like that form, or can it be like I have my answer in like a decimal instead of that?
Well, I probably would ask for your answer in terms of an exact form if I wanted you to go through this method. I would say something like, please use, show your work, show the reference triangle, and explain, find the exact value of secant 7 pi over 6. And then I would say for 30% partial credit, punch it into your calculator and give me the decimal value, as we all know we can do that. But yeah, I know, I mean, fair enough. Like everything of this nature that we're doing, we could just punch into a calculator, right? So the reason we're doing it is just to try to better understand the relation of sine and cosine as you go around the circle and all these things. It's the motive here is really not how to calculate sine and cosine or secant. It's to understand their structure and their relation to different quadrants. That's really what we're after here. So in the same way, like when a person trains for running a marathon, right? They don't just like take a cab because like it's not getting from there to there. It's acquiring understanding of how the running is done. But I know. We could all be replaced by computers. Let's not be like that. How about this, guys? One last example here. Can you find the area? Let's see here. Suppose I tell you that that is 45 degrees. What's the area of that triangle? So what you do, 1/2 base times height, right? So we got to figure out what the height is. Now we know what the base is, right? So this is the base, 10, right? The height, well, right here, right? Here's the height. I'll call it h. That's the definition of height. It's a perpendicular off the base, up to hit the vertex. What you got? You got a 45, 90 triangle, right? So h is the opposite side. I can use sine, right? H is equal to the hypotenuse 6 times the sine of 45 degrees. Now, sine of 45 degrees, we worked out 1 over root 2. So this is like 6 over root 2. So therefore, the area is 1/2 times 10 times 6 over the square root of 2, which is otherwise known as like 60 over 2 root 2 or 30 over root 2. Anyway, you could crunch the numbers, but the main thing I wanted to point out to you is there's a whole wide vista of new word problems we can solve if we can draw right triangles into shapes where they're not already there, right? Like if you can see a right triangle, then you can use the trigonometric ratios to do all kinds of stuff. When I was a three-year-old or 4-year-old, my mom said that me and my brother used to like everywhere she was driving, we go like, "Look, mommy, a triangle." So triangles have a dear place in my heart. Ever since I was little, I see triangles everywhere. I think mostly like whenever there's like you used to have like a lot more poles with electric, right? Anytime there's like an electric pole, there's a guy wire. Like, look, triangle. Always. Anyway, I shut up. See you guys Wednesday.